Welcome to a screencast on an introduction to pH. Now, one way we can quantify acids and bases is in terms of the concentration of the hydronium ion in a solution, or shorthand H+ ion in solution, and this can vary over a really big range. We define something often called the power of hydrogen as the following. pH equals negative log base 10 of the hydronium ion concentration. You've probably heard of pH before, and this is its mathematical relationship, and sometimes we write it in shorthand, pH equals negative log of H+ concentration. Now, the pH scale, we often say it ranges from 1 to 14, but in fact you can have pH lower than 1. You can even have negative pH. You can have pH higher than 14. But most substances probably fall within that general range. And pH is a function of hydronium ion concentration in a solution. And it's a logarithmic, negative logarithmic, in fact, relationship. And so a pH of 1 corresponds to a 10 to the minus 1 or 0.1 molar hydronium ion concentration in solution. A pH of 2 corresponds to 10 to the minus 2 molar hydronium ion concentration, or 0.01. pH of 3 is 10 to the minus 3rd molar, pH of 4, 10 to the minus 4th, and keep on going through, at least on this chart, 10 to the minus 14th corresponds, for that molarity, that's a pH of 14. So notice the huge range of concentrations, and of course we can have higher concentrations out this way and lower concentrations of hydronium this way, but many orders of magnitude range of hydronium ion concentration. On the pH scale, we've made it into just a it looks linear, but it's really not scale. pH of 7 is neutral, and pH below 7 is acidic. The lower it is, the more acidic it is. And a pH above 7 is a basic solution, and the higher above 7 it is, the more basic the solution. Note that the larger the H3O+ concentration, the lower the pH. So as H3O+ concentration gets bigger, pH is lower. And of course, vice versa, as H3O+ concentration is smaller, pH is higher. Now, let's apply this to a calculation. The question is, what's the pH of 0.10 molar nitric acid? Well, the pH of anything is going to be calculated by taking the negative log base 10 of the hydronium ion concentration. So note, we're not taking directly the negative log base 10 of the stated concentration. We need the hydronium ion concentration. Now, in this case, since nitric acid is a strong acid, and since strong acids fully dissociate, then 0.1 molar HNO3 produces 0.1 molar H3O+, and now we can actually use this equation. So in general, we're going to have to figure out the H3O+ concentration. In the case of a strong acid, it happens to be exactly the molarity of the solution, but generally speaking, that's not something we can assume. Well, in this case, it is the case. So negative log base 10 of 0.1 molar is negative log base 10 of 1 times 10 to the minus first, kind of showing explicitly the exponent here. And this happens to be an easy number. Negative log base 10 of 1 times 10 to the minus first is negative 1, which is positive 1. And so with the right significant digits, the pH of this solution is 1.00 molar. If we had a more concentrated nitric acid solution, we can get a pH of 0 or even a pH of negative values as the solution for a more highly concentrated nitric acid solution. Now, what about the other way around? what if we know the pH? Can we figure out the H3O plus concentration? Well, here's an example. Blood has a pH of about 7.40. What's the H3O plus concentration in blood? And the relationship we have is this pH equals negative log base 10 of H3O plus. Now, if we have an equation and we use both sides of the equation as exponents of the same value, it's still an equation. In other words, 10 to the minus pH is equal to 10 to the log base 10 of H3O plus, because the exponents are equal, therefore 10 to each of these equal exponents is also equal. And the reason we did this is that 10 to some power and log base 10 are inverse functions of each other. So they actually essentially cancel each other out, and this reduces then to 10 to the minus pH equals H3O plus, and that is a generally true relationship. H3O plus equals 10 to the minus pH is essentially inverting the pH definition equation and solving for H3O plus is in terms of pH rather than the other way around. We'll apply this generally true relationship to the specific of this problem, which is the pH is 7.4, so 10 to the minus 7.4 equals the H3O plus concentration, and that works out to be 4.0 times 10 to the minus 8th molar. Notice that this equation applies when we use H3O plus concentrations in units of molarity, and the number we solve for, 10 to the minus pH, is going, whatever number we get, that will be the molarity. And when we know a molarity and we take, when we want the pH, we have to have our H3O plus concentration in molarity units before we take negative log base 10 if we want to get the correct answers. And that's it for an introduction to pH.